All right, I'd like to give you a quick introduction into NMR spectroscopy. We've already discussed the details of Fourier transform infrared spectroscopy, and we've been introduced to NMR already in class. I want to give you some information that we haven't had in class about the instrument and the history of NMR to sort of set it in a background of the progress of science, if you will. So sit back and enjoy. So where did NMR come from? Well, let's give a really quick, totally incomplete overview of theoretical physics. Basically, the Greeks came up with the idea of the atom, which was all fine, except it didn't explain everything when we started to look at the details. One of the first details that started to break down the classical view of the world was light. Newton showed that light could break up into colors and be recombined. That was his big discovery, actually, was that you could recombine the colors back to make white light, which meant that white light was actually composed of all those different colors. And Robert Bunsen and Kirchhoff were doing some work, Gustav Kirchhoff were doing some work with emission spectra, and they were amazed to find that certain elements gave very discrete emission spectra. Here's the emission spectra of the hydrogen atom right here. It's the Balmer series of emission lines. And that indicated that, this wasn't just like heat. This was very specific elements of the atomic structure must be giving rise to this. Meanwhile, Kirchhoff was attempting to understand black body radiation, which was basically just the idea of why do hot things give off light? If you heat up iron, it glows red. If you heat it up hotter, it glows white. Red hot, white hot. We know which one's hotter because we understand black body radiation intuitively, or do we? Well, all the theory of black body radiation could fit the data to a certain point, but the closer you got to lower wavelengths, it would diverge from reality, and basically they called this the UV catastrophe. If you followed the classical theory, you'd always end up with infinite amount of UV radiation. But that wasn't what was observed. What was observed was this increase in intensity and then a drop off. And this could not be explained with classical theory. But basically they were able to come up with some empirical equations that described this, but no one really understood the underlying reason for this. And so people were attempting to figure out what really is the underlying physical nature of black body radiation, and classical physics just couldn't explain that. Now, the Greeks, of course, proposed that there was an atom, but what was the atom? What was the nature of chemical compounds and bonding? There was a lot of advance in organic chemistry through the late 1800s, but the exact structure of the atom remained a mystery. And then in 1897, J.J. Thomson was doing some work with cathode rays, and he discovered that that they were a particle from the atom, and he is given credit for discovering the electron. So now we know that atoms have electrons and something else, which the positive part of it. So Thomson proposed this, what they call the raisin pudding model, where there's sort of a positive particle with electrons embedded in it that could be knocked out. A few years later, Max Planck actually finally explained black body radiation using a new idea of quantum physics, the idea that energy could be quantized, that there is these sort of jumps in energy levels. And he didn't really believe in it. He thought he was just using a mathematical, trick to solve the problem. But of course, math is always the truth. And it became clear to him very soon that there was something true about this quantum nature to the universe. 5 years later, Albert Einstein, everyone thinks he was famous for his theory of relativity, and that was important. But in 1905, he published 3 other papers as well, besides relativity. And one of them was on the photoelectric effect, which was basically observing this quantum idea that a certain energy level of radiation was required to knock an electron out of a conductor. And that moved in steps, or quantum steps. So again, the whole quantum thing was starting to come together. Energy and atomic structure seemed to be created in levels. Now, in 1911, Lord Rutherford discovered that basically atoms were composed of electrons surrounding a tiny nucleus, and that most of the molecule, or most of the atom, I should say, was actually empty space. So this was quite a jump in understanding, and this led to a whole other series of models for the atom. And in 1913, Niels Bohr finally came up with a model that seemed to explain everything. It explained the Balmer series of radiation lines. It explained emission spectra. and of course it could go on to explain bonding in molecules. It was a very successful model, and of course Nobel Prize followed for that accomplishment. Now, so we got the Bohr atomic model. Also in 1913, back to J.J. Thomson here, he's not only firing electrons at a screen now he's firing whole atoms at a screen, and he basically has discovered mass spectrometry, and he discovers isotopes. So now we know that there can be more than one kind of nuclei within the same chemical atom. So we're starting to learn more and more about the atom, but none of it explained this fine structure. Look, that line there in the Balmer series, it's actually two lines. That fine structure could not be explained with Bohr's model, which basically had all the electrons in shells. First shell had 2 electrons, second shell had 6, third shell had 10. That was basically, he had these shells. Well, Arnold Sommerfeld, to explain this fine structure, proposed the idea of subshells. And this was the beginning of our understanding of the S, P, and D energy levels within a primary quantum energy level. So we're starting to get a little further along in the quantum structure of the atom there around 2000 or 1916, I should say. Now, Rutherford made another big discovery. He was able to identify that the nucleus of a hydrogen atom was the exact same as a proton. And basically, he's given credit for discovering the proton. So now we found the proton. And remember, proton NMR, that's our most go-to technique in organic chemistry for structure analysis. There was the start of it. We discovered the proton. Now, so we've got quantum energy levels. We've got the first quantum number. We've got the second quantum number. We've described, it's the energy level number 2 has an S and a P suborbitals to it, right? So we got these first 2 quantum numbers. And then, of course, the P orbitals have 3 flavors, don't they? So there's a third quantum number. So we got 3 quantum numbers. But, Pauli, as he's developing his exclusion principle, is trying to explain how there can be 2 electrons in the same suborbital, right? There's 2 electrons in a single p orbital. How did that get there? There has to be yet another quantum number, because it was becoming understood that all of these particles had to have unique sets of quantum numbers. So he proposed the spin quantum number, that electrons had spin. And in 1922, that was strongly hinted at through Stern and Gerlach's famous experiment, where they were able to demonstrate electronic spin in atoms. And of course, Otto Stern won a Nobel Prize for that. Gerlach was left out because you can see the date there, 1943, when Stern won the prize. Gerlach was still fighting for Germany as a scientist for the German side at that point, whereas Stern had fled Germany before the war, and so he was given the credit and the Nobel Prize, and Gerlach was ignored. Now, that's the old quantum age. It still was based on these energy levels and numbers and sort of steps, and everything was something you could draw in a diagram. There was a certain limitation, I guess a certain holdover from the classical world still within the quantum world, and all of that was blown away when Erwin Schrödinger introduced wave mechanics. Everything after Schrödinger has been wave mechanics. Everything's interpreted as wave mechanics. That's when suddenly the sp and d orbitals go from being subshells to being orbitals with positions in space and volumes in space and electron densities in space. So there's the start of the new quantum age. Now, if you can have 4 quantum numbers for electrons, you know what? All quantum particles have 4 quantum numbers, and that's at least my limited understanding. And so there are 4 quantum numbers for particles in the nucleus too, and that's why certain combinations of neutrons and protons are stable and certain aren't. It all comes down to the same kind of things, why certain combinations of electrons are stable and certain combinations aren't. So all of atomic structure is defined at the quantum level. Well, Rabi was looking at the nuclear spin number in nuclei, and he came up with this neat experiment where he takes a molecular beam of ions, and he's firing it through a big electromagnet, and of course a charged particle moving through an electric field will feel the force, generate a magnetic force, and will turn one way if it's one charge, or the other if it's the other charge. So we've got this like magnetic field here, charged particle passing through. You're going to have the force that's going to push it one way or the other depending on its charge. Now, or sorry, depending on its magnetic spin. So you have one magnet interacting with another. So you've got these particles coming through with a particular magnetic spin, and they're either going to, with one spin it's going to go up, the other spin it's going to go down. But then he put a radio frequency coil here that had the same frequency as the energy transition between spins. So basically he chose a frequency that resonates with the energy level between two spins. And he was able to flip some of those spins. So here he's demonstrating that the magnetic moment of nuclei can be manipulated. Now those that didn't get their spin flipped will carry on and just crash into the magnet. Those that did get their spin flipped are going to take the reverse course. And he just puts a detector at the end and he sees how many ions get through. If you're not flipping any spins, no ions get through. But if you keep adjusting this frequency until you get to the same frequency as the nuclear resonance frequency, you'll flip some spins and you will see the detector. So he kept the frequency constant here, and he changed the power of the magnet slowly by changing the current. And so as you change the power of the magnet, the resonance frequency becomes increases with magnetic force. So when you have enough magnetic force that the resonant frequency is exactly the same as the frequency being emitted by this RF coil, you'll flip some spins, and there's his famous graph right there. He's changing the current. We're nowhere near the resonance frequency. We're starting to get into the resonance frequency. There's the resonance frequency. We're seeing beam come through the instrument and hit the detector. As we pass the resonance frequency, we're changing the magnetic field. The resonance frequency is no longer the same as the RF coil. We're no longer getting through and hitting the detector. This was a earth-shaking discovery. Magnetic moment can be manipulated, and that means, of course, it can be analyzed and used. And he won the Nobel Prize in 1944. So 1943, 1944, two important magnetic resonance NMRs, bang, bang. You can see that the world was starting to pay attention to this neat physics phenomenon. These were both, of course, prizes in physics. Now, of course, chemists don't find that useful. Being able to determine the magnetic moment of a mercury ion is not really going to change the world for chemists. But of course, we need to look at the right element. First, we got to find a nuclei that is good for us. And of course, all organic molecules, or the vast majority of them, have lots of protons in them. And protons have a nuclear spin of 1/2. That means they have two spin states, plus 1/2 and minus 1/2. And it turns out that if you have a 1.4 Tesla magnet, which is a perfectly reachable magnetic strength, back in the 1940s, you had have a magnetic resonance frequency of 60 megahertz for the magnetic moment of those ions. So that was the frequency you would look at. Carbon-13 has a nuclear spin of 1/2. And it has a magnetic resonance frequency of 1/4 that of hydrogen. So that's something you could look at. The problem is that carbon-12 is 99% of carbon, and it has no nuclear spin. So no signal. So not every element is NMR active. But you know what? There's usually an isotope of that element that's NMR active, and depending on how populous it is, with carbon-13 it's only 1%, so that's a challenge. Protons are 99.9%. NMR active with the plus 1/2 spin state, so that's a pretty good one to look at. So let's take proton NMR. If we had a sample in a test tube just sitting around, all the magnetic moments, they could just point wherever they want. There's no energy difference for pointing one direction or another, so why would they care? What makes them care is an external magnetic field. So I'm imagining here 17 arrows just pointing wherever they want. There's all 17. They're all exactly the same energy level. So of course entropy is the most important element there. They'll just point wherever they want. Apply an external magnetic field here. And now there's a difference in energy, whether they're lined up with the magnetic field or opposed to the magnetic field. So you see all the arrows are going to pick one direction or another. And why do they pick one direction or another? Because there's these two possible states, with or against. The energy difference between those two states is really tiny. So there's not a huge population difference. I'm imagining that these 17 split into 9 and 8. But really, if there was a million, it would split into like 500,000 plus 1 and 500,000 minus 1 up here. Like, it is a tiny energy difference. The populations are almost exactly identical, which is important when we start to talk about spin splitting later on in this course. So the energy is really tiny here. The frequency, however, is going to be proportional to the magnetic strength. So we have this gyromagnetic ratio. So basically, a number times the magnetic field strength will give you the resonance frequency. So if that was 1.4, basically, if this term here is equal to 42, which is the ratio for proton, 42 times 1.4 is 60 megahertz. So you can predict the frequency from the magnetic field. And the higher the energy difference is between these two lines, because the field is stronger, the greater that frequency will be. And of course, the bigger energy difference I put between these two lines, the bigger population difference I'm going to have, which means I'll have more spins to promote to the higher spin state and more spins to listen to when they're coming down. So I actually get better sensitivity if I can make my magnet stronger. So here's what we have with a typical arrangement of two spins, not much difference in the population, but there is more at the bottom than at the top. And if I should expose this to radiation that is the same as the energy difference between these two states, I can promote spins from one state to the higher energy level. And of course, as they go up, there's a certain rate for them coming down. And when they come down, they emit a quantum of energy of that exact same energy level. So if I'm exposing this to a frequency that's equal to its resonance frequency, it will also be emitting at a frequency that's equal to its resonance frequency. So I can excite and listen. But if I'm frying this with a higher powered radio signal, how do I listen to a very faint signal of the same frequency? I mean, I'm basically jamming my own signal. So NMR, to make it practical for chemists, requires an enormous amount of engineering. So in principle, how might we do this? One way would be to blast our nuclei. Here I've got to basically imagine a sound wave exciting a tuning fork. And if this sound is the same frequency as the tuning fork, it will start to absorb the energy of the sound waves. And then of course, since it's vibrating, it's emitting them. So if you could imagine the sound waves are traveling in this direction, but the tuning fork is emitting sound in all directions, if I had a super directional microphone, I might be able to pick up the sound that's coming from the tuning fork, but of course I wouldn't be picking up the sound that's traveling in this direction. So as long as we're at like 90 degrees to each other, I might be able to pick up only the emitted sound and not pick up the high-powered sound I'm using to excite that vibration. So in some ways, this is like fluorescence spectroscopy. Here's a fluorescence spectrometer. We take a wavelength and we shine it through our sample, and if that wavelength is promoting electrons to higher energy orbitals, where they then settle down to the bottom of that energy orbital level, hang out for a few nanoseconds, and then fall back to ground state, they could be emitting light. And if that light is being emitted, it's being emitted in all directions. So my excitation wavelength goes straight through, and then I'm looking at 90 degrees to that, and I'm seeing the light that's being emitted, and I pick one of those frequencies, and I can get the fluorescence spectrum. Fluorescence spectrometry is really sensitive because I'm looking at, if it emits light or not. I can count single photons with a good photomultiplier, so it's a really sensitive technique. And NMR can be really sensitive too if you design your machine very carefully. So consider this 90-degree arrangement. Another way you could do it would be to blast it with this horn, and then turn the horn off, and then listen. And then you could put your microphones anywhere. You could put a microphone at 90 degrees to your signal source, and also with your signal source. So you could have two microphones listening to the signal. And that's going to be important in modern NMR, which is how we do it. We excite and then listen as the signal hums and then dies away. So how would a modern NMR work? Well, let's go back 50 years to continuous wave machines. Felix Bloch and Edward Purcell were the sort of the originators of NMR that chemists might use. They were looking at nuclear magnetic resonance signals in actually bulk materials. Purcell was looking at paraffin, and Bloch was looking at water. But what really excited the world was the NMR of ethanol. There's the NMR of ethanol in 1950. And that was, of course, collected on an oscilloscope. They didn't have convenient NMR machines. This was still a tool of physicists. You had a big thing cobbled together in a laboratory, and wires everywhere, I'm sure. And there's the signal for ethanol. And now, of course, everyone knows ethanol has three kinds of protons. Look, bing, bing, bing. So suddenly it became obvious that you could interpret molecular structure with NMR. So shortly after that, Bloch and Purcell won the Nobel Prize because this is becoming obviously going to become a very important technique to physics and chemistry. So how would we construct a magnet? Well, you could take two big permanent magnets. This is one way to do it. So first of all, you got to manufacture these magnets, and they have to be perfect, and they have to have perfectly flat faces to try and make the most perfect field between them as possible. They also have to be pretty big because at the edges the magnetic lines are going to be curved, and in the center, of course, they'll be straight between the two surfaces of the magnets. And you have to put them in a sturdy holder that's not magnetic, that can keep them at the exact correct distance from each other. And if temperature differences are changing the size of your materials, and the exact parallel nature of these magnets is, say, drifting a bit, you would have to actually hammer wooden wedges down between the holder and the magnets to shim the magnet. So the word shim comes from a time when you would actually physically be moving these magnets with screws or with wedges to try and make the magnetic field as perfect as possible. Now, of course, by 1960, when the instrument that I'm going to talk about comes about, they'd figured out how to do that electronically. So you wind some wires around your magnets to add just a little bit of electromagnetic character to this so that we can alter the field a little bit. And then we just slide our sample between the magnets, and we have our sample in an external magnetic field. Now, if we blow up the diagram a bit, inside I have a transmitter that's transmitting at the resonance frequency that I'm interested in. There's 60 megahertz. And then I have a receiving coil that's at 90 degrees to the transmitting coil. Now, those of you who have studied the physics of radio waves know that the polarization of the radio wave is important. You have to design your antenna to take that into account. Basically, if a transmitting antenna cannot receive or cannot send a signal to a receiving antenna that's at 90 degrees to it. And right here, they're right next to each other. There's no chance for the polarity of that signal to change due to refraction around corners or hitting walls or anything. So basically, this receiver will not receive the powerful signal that's coming off of this transmitter. But the sample receives it. The nuclei are getting excited. If the magnetic field strength is such that their resonance frequency is 60 megahertz, they'll receive the signal and emit it. So if I slowly change the magnetic field by changing the current through these wires, I can basically travel through a range of possible signals for all the proton nuclei in that sample. So as I sweep the field, going from a strong field, or from a weak field, I should say, to a strong field, from down field to up field, I will go through all the possible frequencies. And as I pick up, every time we cross 60 megahertz for a particular pair of nuclei, or a set of nuclei, we'll get a signal. So this is where the term chemical shift comes from. The chemical shift is related to the magnetic strength that I had to set in order to get 60 megahertz. And the first NMR to do this was the famous Varian T-60. And this is what made their money and made them famous. Number one, it was small. I mean, NMRs up to that point were, as I say, designed by physicists for physicists, big room-filling contraptions, magnets that were open to the world. Notice how everything's all contained here. The magnet's in here. You drop your sample in there. There's your console. This platen here, which holds the pen, as that moves across, that changes the current that goes through your wires wound around your magnet, so that changes the magnetic field. So basically the x-axis here is how much you're changing the magnetic field, and the y-axis is going to be controlled by your receiver. If there's a signal, it's going to come up. Now you have to start at one end and gradually and slowly go across, because it takes time for the signal to be absorbed, and it takes time to emit it. And if you're moving too fast, you'll basically pass through the signal so fast the pen will hardly move. So you have to move that pen basically about a second per hertz of frequency. So if you're sweeping 600 hertz, which would be a typical spectrum here, it would take a 5-minute sweep to get a really good NMR. So it takes some time to do NMR like this. But there's the output you would get. You would start here at a particular magnetic field strength and keep going. And these particular protons in this ethyl group here are now we're catching their resonance frequency. And we see them, and then we carry on down there. So that's how we can detect our signals with a continuous wave instrument. So here is a Varian T-60, a slightly more modern model, 1968. Recognize that magnet? That's the magnet we're still using, although we have modernized it to a fully modern Fourier transform system. We're still using our old T-60 magnet for our undergraduate research program. So here is a typical spectrum for bromopropane. We see this peak here is going to be split into 7. Of course, the two methyl groups only see that proton between them, and they'll be split into a doublet. I start the magnet at a particular magnetic field strength, and I slowly increase the magnetic field strength as the plotting bar moves across. And when it finally gets to a magnetic field strength where this proton here, which is a little bit deshielded, is finally starting to feel enough magnetic field to precess at 60 megahertz, it starts to absorb and emit the frequencies. And the same thing happens again over here. We get to a more shielded one. We need a stronger magnetic field before it feels enough magnetic field to precess at 60 megahertz. But finally, the magnetic field that these nuclei are feeling is such that they're at 60 megahertz, and I get a signal. And then for the slightly lower split signal there, and then that dies away. So we started at a lower field strength, and we ended up at a higher field strength as we went from downfield to upfield. And that's where the word downfield comes from. It comes from the old-fashioned continuous sweep NMR. So here's an old blast from the past. This is from the 1960s, early 1960s. We have a 0.9 Tesla resistive magnet, so that's a pure electromagnet. That'd be a 40 megahertz magnet. There's the chart recorder for collecting your signal. There's your frequency generator and all your electronics, and I presume that this is the power supply for the whole thing. Of course, the T-60 was quickly became the #1 seller there for Varian, and they were selling continuous wave instruments like crazy. They were like having a great time selling continuous wave instruments and not really thinking about the future. Why would you when you're selling continuous wave instruments like crazy? You don't have to innovate, or do you? Well, let's talk about how to improve our signal, because of course chemists want a better and better signal, and as we're going to see, the way to do that is a more powerful magnet. But you just can't get past about 100 megahertz magnet for NMR. A permanent magnet really can't be made any more powerful than that. Electromagnet's not much more powerful than that because of problems with, well, physics. I can't even get into it. It's over my head. Just trust me. The physicists said you couldn't do that, and I believe them. So we had to turn to superconducting magnets. So let's briefly talk about superconductivity. Tesla, back in 1900, noticed that if you cooled wires down, they would conduct electricity better. Now, he couldn't get cold enough to observe superconductivity, but you know what? If he could have, he would have been the one that discovered it, because he was on track. But really, it took a technological leap. James Dewar was, in the 1890s, was liquefying gases like nitrogen and oxygen, but even he couldn't get cold enough to liquefy helium. And it took until 1911, when Heike Oens actually liquefied helium, and it wasn't long after that that he discovered superconductivity. Because what was the first thing you do? Everyone knows that wires conduct electricity better at lower temperatures. You just start to explore that, and suddenly, bang, superconductivity. He went to a point where just instantly he saw mercury become a material with zero resistance to electricity. And of course, you get all the freaky quantum effects that come out of that, like the magnetic levitation and all that sort of stuff you have with superconductive magnets. Now, no one understood why. This was, of course, it's all due to quantum physics, and it took a while before that became understood, but Cooper, Schrieffer, and Bardeen proposed a theory, a quantum chemistry theory, or quantum mechanics theory, I should say, that explained superconductivity, and they, in the 1950s, and they were rewarded in 1972 with a Nobel Prize for that advance. It's the second prize in physics for Bardeen. He already won one for transistors, so he's the only double Nobel laureate in physics, so he must be a big deal. Continued development. Mercury is not so useful for an NMR. If at room temperature, it's liquid, so how are you going to transport that from one place to another? But other materials can be made superconducting, and Hake and Berlincourt here developed a niobium titanium alloy, and the beauty of that is it's ductile. You can stretch it and work it and maneuver it, and so you could make a wire out of it. And basically, I would say that most moderately powerful superconducting magnets today use this superconducting material. Now, flash forward to 1987, and Bednorz and Mueller in 1986 discovered some ceramic-based superconductors that could be superconducting at liquid nitrogen temperatures. You didn't have to go all the way down to liquid helium. And of course, over the past 20 years, great advances have been made in that field, and superconductivity has been rising in temperature quite a lot. They reported this in 1986. They won the Nobel Prize in 1987. That's how big of a deal that discovery was. And if you're designing a superconducting magnet today, you might use one of these ceramic materials. You can kind of make a tape out of it, or you might use a wire. And I'm going to discuss the wire construction that's in most superconducting magnets that I'm familiar with. You have a copper wire that is embedded with filaments of the niobium titanium alloy. And You try to use as many tiny filaments as possible because superconductors do not let a magnetic field exist inside them or an electric field. I'm not really up on the physics, but I can tell you that it's all about surface area. The more surface area you have on these coils, the more current you can put through. So you need a lot of thin ones embedded in copper to have a lot of surface area. Now you would say copper, that's a conductor, but it's not a superconductor. So once we cool this down to 4 degrees Kelvin, the niobium titanium, actually at 10 degrees Kelvin, it's a superconductor. So at 4 degrees Kelvin, liquid nitrogen temperatures, or sorry, liquid helium temperatures, it's a superconductor. The copper is almost a superconductor, but not. Its resistance is really low, but it is not zero at that temperature. So the copper acts as the insulator, and the current runs through the superconducting filaments here along the surface of each one. Now, if your magnet should ever warm up, and these lose their superconducting power, what would happen to all that current that's flying around inside your magnet? Well, it could then start traveling through the copper, which will release a lot of heat, but at least it won't explode from all those electrons stopping instantly. They'll heat up the copper and come to a stop. Because the way you charge up these magnets is you hook it up to a power source, you start loading it up with current, and getting that current zipping around here. No, zero resistance, so just keep loading it in. Load in as much as you want. There is a limit, of course. And once you've gotten the magnet as full of current as it can handle, you open up this circuit and cut off the power, and you short circuit the magnet. So the current's going to go through those coils, back up here, back through the coils, back up here, back through the coils. And so now, without the battery source hooked up, the current is just flowing in there, nothing influencing it. It just evens out, spreads out, and it's just spinning around there, making a superconducting magnet, and it creates a nice homogeneous magnetic field, not influenced by any frequencies from your power source. So that's how you might construct a superconducting magnet. And once you've got one, look at the improvement. Here's a 60 megahertz NMR down here. Here's a 300 megahertz NMR. So this is our bromopropane. And notice how wide this signal is compared to here. That's because the signal width is defined by the coupling constant, and that makes this signal 41 hertz wide. But each part per million of the signal here is 60 hertz here. 1 part per million of 60 megahertz is 60 hertz. But 1 part per million of 300 megahertz is 300 hertz. So we're going from 60 hertz for a part per million to 300 hertz. Now, that's because the energy levels between magnetic transitions depend on the strength of the magnet. But splitting only depends on the strength of the magnetic moment of the protons themselves, because splitting is due to the proton magnets talking to each other. So this magnet does not change its strength, and it's going to split that magnet there by a certain amount. And so this is 41 hertz wide here too. 41 hertz out of 300 hertz looks a lot narrower than 41 hertz out of 60 hertz. This is 2/3 of the spacing between a single part per million, whereas this is a lot tighter. Now, that's all nice, but both of these spectra are easily interpretable. But what happens when things get more complicated? Check out this one here, this phenol derivative. The splitting that we see between these 3 non-equivalent protons and this pair of protons and this pair of protons, they're all kind of, well, the aromatic protons are really close to each other, and we have these distortions, plus one set of peaks is on top of another set of peaks here. And that leads to things getting kind of, well, I don't know, what's the word? Complicated. And no one likes complicated. What if we use a higher field magnet, and the chemical shifts of these peaks is not going to change? Notice, look, I'm going to start here. The chemical shift of that signal, which goes from here to here, does not change. It's 24 hertz wide. There it is, 24 hertz wide. But now it's pulled in nice and tight out of the other signal. And these signals become a little better behaved. Second order splitting, which leads to this distortion, is reduced because the peaks are now farther away in hertz from each other. And we'll talk about these kind of effects later on when we're talking about spin-spin splitting. So the message is a higher field magnet gives you better NMR, better signal to noise, narrower sets of peaks, gets everything out of each other's hair as much as possible, and just in general is easier to interpret. So the highest field magnet you can get, the better. And so if you had $15 million, you could get this Bruker 1 gigahertz magnet. Now this is the kind of magnet that you don't just buy, you have to buy the magnet and the building you're going to put it in, because it's probably going to be a little too big for your shop. But if you're going to invest $50 million in this magnet, that won't be a problem. This is the kind of magnet you would want if you were looking at really complicated structures like, oh, I don't know, proteins. So how would you construct a superconducting magnet? Well, you need a tank that holds liquid helium. You need your solenoid in that tank. And down through the tank, you have a tube that's at room temperature, so it's insulated as well. And in that tube, you could lower down your sample. And from the bottom, you could rise up another tube that contains all the electronics for your NMR. Now, that's sort of a simple diagram. There's your sort of electronics. You could pull that out and put in a different one. Could, as things improve, put in an upgrade pretty easily, or a probe meant for an entirely separate purpose. The permanent part of your magnet that you can't change, of course, is the magnet itself. And then your sample can be lowered down and raised up and changed whenever you like. This is sort of a fairly advanced superconducting magnet right here. You've got your liquid helium that surrounds the magnet. This liquid helium, however, is surrounded by another layer of liquid helium. This inner layer of liquid helium is being refrigerated to 2 degrees Kelvin. So the heat's being pumped out of this into this. So it's even colder for higher performance. That's quite amazing. Our magnet just has regular liquid helium in it. Outside of the liquid helium is a bath of liquid nitrogen, because the lower the temperature difference, the better your insulation is going to behave. So you'd rather your liquid nitrogen boiling off than your liquid helium. Of course, your liquid helium is boiling off as well. You'll have to replace your liquid helium every so often. You've got to replace your liquid nitrogen once a week. So basically, we have a sophisticated Dewar flask with our magnet in there. And lots of electronics, and that's why these NMR cost so much. Speaking of electronics, there's our probe. We would put that up the tube, up the center. Your sample's going to come down from above and go into this part of the probe here. And here's where all the electronics are, and this is where all the control is, and this would be connected actually to more sophisticated electronics controller boxes that are just outside your instrument. So we've come a long way. We've gone from there's the first Fourier transform NMR, the Bruker WH90, and we've gone all the way now where you could buy this sort of everyday 400 megahertz Bruker NMR, and that would fit easily in any room in your chemistry department. A heavily shielded magnet, it's not going to mess with anyone's computer screens. And you can get all the way up to a 1 gigahertz magnet. And of course, the bigger you get, the bigger you get. So once you get into these big, powerful magnets, you're going to need bigger rooms. And this is all in the catalog. All you need is a checkbook. Now, we can generate a signal and we can listen to it with all that sophisticated electronics, but what do we do with it? We've already sort of introduced the idea of Fourier transform when we talked about IR spectroscopy. So here we have basically imagine a violinist playing a single note. Hum. And if we did the Fourier transform of that single note, we would get a single frequency. The Fourier transform is just a mathematical method for converting amplitude up and down over time, so we go up and down as time goes on, to frequency. Amplitude, that doesn't change, but now that's the frequency. So this went up and down so many times a second, right? Well, there's how many times a second it went along. So it's going to turn this into a list of frequencies and their amplitude that are in that signal. And now this signal, if this signal was constant and went on infinitely long, this list would contain a single sharp line that contained the exact frequency. But if you don't have an infinite set of data, depending on how long the signal lasted, Fourier transform is going to give you a particular line width. The more data you have, the narrower your line width. Now, if you had more than one frequency in the signal, say a violin quartet playing a chord, you could Fourier transform it and get all the notes of that chord as a list. Maybe that's the G major chord. Now, so we have this ability to turn signal into frequency lists. Now in NMR, however, it's a little more complicated. We hit our nuclei with an intense radio frequency pulse. We turn it off. Now that's a major feat of engineering right there. I need a transmitter that can go from 0 to 60, bang, instantly, last a set duration, and then turn right off. And that is very sophisticated electronics. And then I need to listen to a very faint signal with as little noise as possible. Also very sophisticated electronics. But this is what I record. Just like hitting a bell. Ring! And the signal dies away. That's called free induction decay. The signal is going to die away as things return to their ground state. And because of that, this decay pattern limits the amount of data we can get, because eventually the signal will be 0. So the better your magnet is, the better perfectly shimmed your magnet is, the longer this will last, and the narrower your peaks will be. But if I listen to this the Fourier transform, or listen to this frequency and I Fourier transform it, I might get this NMR. So Fourier transform converts the signal we're getting into the spectrum that you see. My eyes can't get any information out of this, but my eyes can see lots of information out of this. Now, electronics have noise in them. You hear that, you listen to the radio hiss on an old-fashioned radio. And so, of course, a signal might be noisy, especially if there's very little signal, if you have very tiny peaks or a very small amount of sample. So if you have a lot of noise in your signal, you're going to have a noisy Fourier transform. But David Felget observed, and he developed, was a major person in developing Fourier transform IR. He realized that if you add a whole bunch of signals together, the signal's always there, but the noise is random. So eventually the signal comes to dominate the noise if you just keep adding them together. So here's an example of adding doing 100 different experiments on the same sample and averaging all the data together, and look, my noise went from this to this. And wouldn't that be a huge improvement to go from this much noise, compare this to this. All you have to do is run your spectrum or run your instrument overnight. So if you just did a handful of measurements, you could get this kind of a signal for carbon-13 spectra, but the more data you collect, the better it is. The only limit to how good your signal is time. So of course, time's not free, so you have to plan ahead. Now, as I finish, I'd just like to point out that none of this was done in the absence of people. There are important people throughout the history of NMR, not just the people who developed the physics of it, but the people who actually made the instruments. And this is a big business. There are people out there making instruments right now, and these could be people who you might choose to emulate and model your life after. But I would say, give up now, you will never be as cool as the Varian brothers. Russell Varian and Sigurd Varian started Varian, the company that made the first commercial NMRs. Russell, they both grew up in a utopian community in California called Halcyon. It was some type of a commune. And then they went on to greater things after that. Russell had a learning disability. It was only through sheer force of will that he was able to graduate university, and then he went on to do a master's in physics, but he did not get accepted into a PhD program. So he had to go off and actually start doing stuff. And what he did was he invented the klystron, this device right here, which is a microwave emitter. Sigurd started college, but he just couldn't stand it. He was just bored stiff. So he went and became a pilot, and he became a pilot for American Airlines back in the early 30s when they were starting to develop routes into Mexico. And so he's flying into Mexico, and he notices the maps are all wrong. So he's basically correcting the maps as he flies and basically mapped the flight routes for American Airlines in Mexico in that time. Now in that time, Russell had developed the klystron, and Sigurd was very handy with his wrenches and tools, and he actually built it. So they together made this device. Now microwaves at that time were created in much larger machinery. So radar, which was being developed in the late 1930s as a military weapon, it was intended to fry pilots in flight, but they just couldn't get enough power to cook enemy planes. But they did, of course, start to notice that they were receiving reflections off those planes, and quickly it turned into a detection method. But it still required large land-based systems. You couldn't put it on an airplane, so how are you going to get it out into the ocean so that you can sink U-boats with it? Well, they developed the klystron, which could be put on airplanes, and together they are probably responsible for sinking more U-boats than anyone else. They're also good friends of Ansel Adams, who took this picture. So yeah, there's lots of interesting stuff about the Variants. They started Varian to create electronic equipment. It's always had a role in television and communications. But then Russell became interested in, just as a hobby, in nuclear magnetic resonance because it required microwaves, and he had a microwave generator right here, and he understood microwaves. So just out of interest, he began to dabble in NMR, and the continuous wave NMR was born. Now, Varian was becoming quite successful, and they had some money to throw around at pure research, and so they hired Richard Ernst, Weston Anderson, Ray Freeman. These people were coming out of universities with big ideas about nuclear magnetic resonance, and they were coming to Varian to work because that's where the business was. That Varian was one of the companies that started Silicon Valley, and these guys were joining the startup, if you will. Ernst, Anderson, and Freeman collectively worked together and developed Fourier transform NMR. Russell Varian himself had the idea, but he had the idea 10 years before you could do anything about it. The equipment wasn't quite there. But Ernst came up with the idea of using a narrow, high-powered pulse to excite all of the nuclei of a molecule at the same time. So sort of a broadband technique, you're hitting them all, getting them all excited, and then you'd listen to the signal as it dies away. But then you had to do the Fourier transform, and that required a computer. And they would convert that information from their instrument into punch cards. It was a whole truckload of punch cards. They had to take that truck and feed those punch cards at night into an IBM computer several miles away and get the Fourier transform done. Now, Varian wasn't interested in Fourier transform NMR, and they kind of let the project die. And Ernst went back to Switzerland. And wouldn't you know it, a few years later, a company in Switzerland named Bruker started producing Fourier transform NMRs. Now, Ernst was still connected with Varian, and most of his inventions were patented by Varian, and he was a Varian guy. But he's in Switzerland, he's training students. Where do you think his students were going to work? Bruker. And they were developing Fourier transform NMR. One of the major drivers of Fourier transform NMR development were Gunther Laukin, who started Bruker, and Anthony Keller, who was a physicist who had a lot to do with the early Bruker instruments. And Bruker developed the first commercial Fourier transform NMR, the WH90. Now, Varian felt that Fourier transform was unimportant because everyone was buying their continuous wave instruments like crazy. They were making money hand over fist. They just did not see, shall we say, a consumer interest in anything more. So why would you give it to them? Well, as soon as the Fourier transform came out, 2 years later, no one was buying continuous wave anymore. It was just so much better. And so Varian was caught with their pants down. Another important innovator is the Fourier transform itself. Now that requires a computer, enter IBM, and the Tukey-Cooley fast Fourier transform algorithm. It was a recursive algorithm that was computer friendly for doing the Fourier transform. It had actually been developed 100 years before by Carl Gauss, but he wrote it into some obscure journal in Latin, and no one even knew he did it. It was only discovered by historians afterwards. But the Tukey-Cooley algorithm was designed to be run in computers, and that's, of course, why the first computers to run Fourier transforms were IBM computers. So the fast Fourier transform algorithm was really powerful because it did all the math in the same memory bank. It overwrote the data with its own Fourier transform. It was a recursive algorithm that kept on improving things like that bit by bit. And you only had to use as much memory as you had data. You didn't have to have a memory bank that had your data and something equal in size to write the answer into. And memory back then cost $1 per bit, and that was in 1965 dollars. So you can see how that was important. Now, Varian didn't take things sitting down. They invented the superconducting magnets that we know today in response to the challenge. And they started developing high field magnets and getting past the 100 megahertz barrier. But then you know what happened? The business geniuses that were running Varian, the MBAs, they said, why are we making our own magnets? That costs money. We can just outsource that and buy commercial magnets. So they stopped innovating. And who ate their lunch again? Bruker. And in 2010, they were purchased by Agilent. And in 2014, Agilent shut down the NMR division that they had purchased. And Varian is no more. So there's only Bruker and JO left, which is a Japanese company making NMR. So hopefully competition will continue and prices won't skyrocket. So that's sort of a brief overview of NMR and where it comes from. We had to work through years of quantum physics advances until we came to understand nuclear spin, and then we had to come to understand how to manipulate that spin, and then we had to build instruments that could measure that spin, and we had to make them perfect enough in order to get decent signal. And then we came up with the Fourier transform technique, which of course is the modern method, and it's so versatile and so useful. And Ernst over here, who won a Nobel Prize for it, and I really think that Anderson and Freeman should have shared that Nobel Prize because he won it for developing Fourier transform NMR. But I can see why he won it alone, because he alone went on to then develop two-dimensional NMR with Jenner from Belgium, and he also was instrumental in developing MRI imaging. So if you wanted to give a NMR a Nobel Prize to someone who represents modern NMR, I can see why perhaps the Nobel Committee had chosen Ernst alone. But these two guys were intimately involved in the development as well. And so there's a rich history of NMR centered around Varian, and it all went to dust. They sold themselves to Agilent. Agilent bought them for $1.5 billion, and then 4 years later threw the whole division in the trash. And the only people out of a job were Varian engineers and scientists. The brilliant managers at Agilent who threw away $1.4 billion, no one got fired. Anyway, that's modern business. Only people who get hurt are the workers. So watch out. Anyway, that's where NMR came from. Here is where most of the diagrams and pictures that I've shown in the presentation came from. So if you're interested in any of these and want to look at the sources, there's the references. Have a nice day.